Okay, so now let's talk about some of the challenges like in solving RL, like which is not just learning value functions or policy, right? Like so now when we introduced most of these algorithms like that we discussed before the break, like so we started with tabular methods, right? Like so in the case of tabular methods, like there is no question of like state representations because states were just represented by indices, right? Like so like often we work with grid worlds, like so where let's say I have a 4x4 grid, like then states are just indexed as 1, 2, 3, 4, 6, 7, 8, and so on. And my algorithms, like for example, let's say I'm learning a value function, then I was learning value functions in tables, like where each row is a state, and like depending on whether I am learning state value or state action value, like I would have many entries like in this row, right? Like so, like for example, if you're learning Q value with 3 actions, then for each possible state, you are trying to learn like and maintain an estimate of Q values, right? Now, this kind of tabular approaches like work for simple problems, but for a lot of interesting problems, like the number of states is exponentially large, so tabular methods are not going to be efficient. So this is where the idea of like representation learning for all. Sure, right? Like so now one way to learn representations is to use function approximations, right? Like so we can have, like for example, a neural network which takes the current observation in whatever format. Like so, for example, in the case of Atari games, like so we had the image given as input. Now, even in the case of a robot, like so maybe like the input state is all the like joints and like so angles and like speed and torque and everything, like everything that you can get from the physical robot is fed as input. Okay. Now, once you have this, then you can use a neural network, like for example, like to learn a good representation, and from this representation, you try to estimate the value or the policy. Okay. Now, there are a lot of advantages with representation based, like these kind of function approximation based methods. Like so, like for example, like with function approximation, like so, first of all, you can scale, right? And you can also learn to generalize, which is not possible with tabular approaches. So we are going to talk about generalization in reinforcement learning today, but like there are many types of generalization, okay? But this is probably like the simplest type of generalization, which is, can I generalize from like one state to another state? Which means after learning from a bunch of states, given a new state, like can I take an action, like an optimal action, even though I have never seen this state? Now, if you take the tabular approach, for example, let's say you have seen all these states, but you have never seen these 2 states. Now, there is no way in which you can have an estimate of the value for these states in tabular approach. Okay. On the other hand, let's say you have a neural network which takes a state and tries to learn the value of the state. Okay. Now, this neural network, you can train this neural network with a bunch of states, or you can feed in a totally new state which you have never seen before. This is going to give you some estimate for the value of the state. Okay, it might not be the best estimate, but it is going to give you some estimate, right? Like so, in some sense, like you can easily generalize, like if you are using function approximation. And apart from scaling and generalization, are there any other benefits of function approximation? Anything else? Okay, so there are some answers in the chat. Okay, I think the answer is more about state aggregation. Like, well, it's kind of a naive function approximation, right? But that is what I mean by scale here. Well, there are also other benefits, like, so for example, like with a function approximation, like you can kind of easily handle like continuous action spaces, right? Like, so like you could have an estimate of the mean and variance of a Gaussian, and that is going to give you the continuous action spaces, right? Like, so, well, it doesn't mean that you cannot handle them without function approximation, but it is just that it is easier. There might be many other benefits. Okay, so now function approximation is about better representation, right? Like, so now there is also this bigger problem of like learning good representations itself, right? So which probably we did not cover in this course. Okay, so what is representation learning? So representation learning means that, let's say you're interacting with the environment, like, so can you learn a better state representation so that it becomes easier for learning the policy or value function on the top of it. Okay, now there are two ways in which you could do this. Okay, so the first way is like the function approximation route, like where like you have a neural network, like which takes the state and passes through a bunch of layers. You have the hope that one of these layers is going to have a good representation of the state. Okay, now in this case, the learning is still through reinforcement learning. So however, there's nothing stopping us from like learning better representation separately or simultaneously with reinforcement learning. Okay, so like for example, like you could think of pre-training as a way to learn representations like before you start solving the task. Okay, like a simple pre-training that you could do is just forward prediction. Like, so like let's say you have access to an environment, like you want to learn the policy. Okay, typically if it is an image based problem, then you'll be using a convolutional network, like which takes the image in and produces some representation, right? Like, so you take the image and you pass it through a CNN, and CNN gives you a final vector, and then you can probably learn the Q function if you're using, let's say, DQN. Okay, now one way to decompose this whole pipeline is like the CNN here is really trying to come up with a good representation. Okay, on the top of this good representation, you have like one linear function approximator, okay, which is learning the policy, or in this case, the value function. Okay, now you need to interact and use Q learning update to learn the Q values. Okay, you don't need that for learning the representation, right? Like, of course, it is useful if you're learning the representation directly through the Q values, like, because you are learning a representation which is going to be easier for solving the problem. But you can also learn this representation in other ways. Okay, like one simple way in which you could learn this representation is by using the idea of forward prediction, where given this is basically learning the model of the world. Okay, so given the current state and action, you just predict the next state. Okay, now again, to do this with this deep neural network setting is like I could take the current state, which is the image and the action. Okay, and it is passed, let's say this is passed through a CNN, and the representation is taken and the action is added. Okay, now I can try to regenerate, like generate the next state. Okay, so given the current state and the action, we are interested in predicting the next state. The next state in this case is actually an image. Okay, so you can use something like deconvolutional network, which will generate ST plus 1. Okay, but of course, if you have a vector representation for the state, this is very simple. Like you have an MLP which takes XT and AT and just tries to predict ST plus 1. Okay, so this figure that you see here is for images. Okay, but the general idea is like you execute some random policy in the world, which means you're going to collect more and more transitions. Okay, now you learn a representation using this transition. Now you can use this CNN that you learned from this representation to actually initialize the CNN that you see here, like in the actual DQ, right? Like so, this is the idea of pre-training. Is that clear? Now there is also another way in which you can learn the representation, which is through the idea of auxiliary tasks. Okay. Now the idea of
I'm not clear about the advantage of the forward prediction. So you learn part of the neural network that is predicting the next state.
Yes.
It has nothing to do with the reward, right?
Yes. No, but here you are just learning a good representation for the state. You are not learning to predict the value function.
So when in the final network, other than speeding up the computation, is it doing anything? Or
it's just speeding up. Yeah. No, yeah. Oh, okay. This doesn't mean, well, like, I'm not sure if it is just speeding up. Like, so when you have poor representation, the learning problem is harder. Okay. When you have good representation, maybe the learning problem is going to be easier. So you can also get, it is not completely true that speed up, but you're going to get the same performance. Maybe your performance could also improve. Like if you have a good representation to learn the policy on.
Yeah, but like this is like a completely different problem, right? So on the while that network, you care more about learning the representation, which gives you a better reward.
True. Okay, so that is why I'm not giving any guarantees here. Okay, and also like this idea of forward prediction is just one of the many examples of like pre-training for reinforcement learning. Okay, so like you could do other objectives like so. Forward prediction is one objective. Okay, and it's actually one of the most common objectives. So typically, like when you have a good sense of what is like the dynamics, like it is going to help you with your value estimation on other problems. Now this is an assumption. Okay, so as you said, like sometimes it might hurt. Sometimes like forward prediction model is not the best representation for you to learn the value function, but most often it is useful. Okay, but there are like many other approaches to solve, like to come up with better initialization. Like so, like we are going to talk about like transfer learning in reinforcement learning, like so where you will learn a representation by learning a policy to solve one task, and then take that representation and start learning a policy for a new task. Okay, so that is another example of like pre-training. So there are many ways in which you could do this. And the second way in which you could have good representation is through the idea of auxiliary task. Okay, so what do I mean by auxiliary task, right? Like so now, like for example, like instead of doing forward prediction as a separate first stage and learn a representation and then use that for my DQN, right? I could consider this forward prediction objective as just an extra auxiliary task for my reinforcement learning agent. Okay, so now I just add more goals to the agent. So the primary goal of the agent is to predict the value function if it is DQN. Okay, if it is actual critic, its primary goal is to predict the policy. Let's just take DQN as a running example. Okay, so like the primary goal is to predict the value function, but I can add extra tasks, okay, which are with the hope that they're going to be useful and they're going to guide the process, like by giving better representation. Okay, so in this case, like given a state, okay, now I have a CNN, okay, which tries to predict the Q value, right? Now, I could also have an auxiliary task here, like which is taking the state and with an action, okay, have a decon network to predict ST+1. Now, this CNN that you're seeing here, this is shared by both the policy, both the value network and also this like forward prediction model. Okay, so it gets gradients from both the directions, and again, assuming that they are going to be in the same, like they're both going to help like moving in the same direction, like so you're going to learn faster. Okay, but sometimes it could hurt, like there is just, we don't have a general guarantee that this kind of pre-training or auxiliary task is always useful. Okay, but these are kind of the most practical solutions that like you would encounter in several deep reinforcement learning work. Is it clear? Yeah.
So we are assuming that estimating the Q values is like kind of helping in also predicting the next state.
Yes. Oh, well, we are assuming that this forward prediction is helping us to come up with better estimates, like better value estimates.
But it doesn't mean that when you predict the next state, when a model predicts the next state, it could also mean that it's predicting the Q values better.
Yes, it doesn't guarantee that. It doesn't guarantee that. So in fact, like for example, like you will see a lot of other auxiliary tasks in the literature. Okay, so predicting the next state is one of the auxiliary tasks. Like now you could generalize this to like predicting next n states, right? Like or like which is kind of like an n step forward model, right? Or you could try to predict along with the Q function, like you could try to predict what else, like so, like for example, like there is a lot of work in self-supervised learning literature, like so where like you can try to predict things within the state. Like so, for example, like given the state, like can I predict like how to fill part of the image? Like so, if I have only the rest of the image, right? Like so you can construct your own tasks which are going to give some feedback and some gradients and help the learning process. Any questions so far? Yeah.
If you are separating the auxiliary tasks, so the main network is going to calculate the key values. So what is the downstream task that you can use it for?
Okay, that's a good question. So here's the thing. Typically, when you treat like this representation learning as an auxiliary task, right? Like so, we don't really care about the final performance of like forward prediction. Like we will always care about the final performance of like the task that we care about, which is estimating Q values. Okay, so you will do a bunch of auxiliary tasks, but in the end, like once your training is over, like you will just take the Q network and execute the policy which is based on the Q network. So however, like there's nothing stopping you from using this forward prediction to do planning with Monte Carlo research, right? So but it is just that maybe it is not the best forward prediction model, like because it is not the primary goal of this architecture. Any any other questions? Okay, so this is about learning good representations. Okay, now there are also other issues in like solving reinforcement learning, right? Like so probably that's the second issue. Like, we can talk about partial observability, which is something that we have already covered, right? Like so, like you can have function approximation, you can have good representation, which is going to scale up things. Okay, still you're going to have trouble, like if you cannot observe the entire state of the world. Okay, and for most of the real life problems, like the world is partially observable, which is also true for a lot of like robotics tasks, or in general, even Atari, like if you don't do frame stacking, right? So now, how would you handle partial observability? So I think we discussed about extending MDPs to POMDP setting, right? So which kind of constructs like a new MDP, like based on by integrating, like by adding the fact that the world is partially observable, and like we discussed about how to extend the existing algorithms to the POMDP setting, right? Like, so we looked at POMDP Q learning, which is an extension of MDP Q learning, right? Now that is more on the theoretical side, but on the practical side, like so if you want to do if you want to handle partial observabilities, like so we would use RNNs, which is a kind of function approximator that integrates information over time steps, and at any point, like you are conditioning your policy on the entire history, which means that hopefully like you have less partial observability. Okay, but even conditioning on the entire history doesn't guarantee that you have the state representation. So but we are kind of relying on the fact that sometimes you don't need to know the entire state representation to take optimal policy, but maybe most of the times. Okay, so there's only like some relevant part of the state which is required to know to take action, and as long as you get that part like represented in your state, like in your observation, like then it is all good, right? So with partial observability, we actually differentiate between observations and states. So states are the internal representation of the world, like the complete representation of the world, while observations are just what you see, right? Like so, like observations come from the state, but we don't know how they are constructed. So they just have partial information about the state. Yeah.
So you talked about frame stack.
Yes.
So are frame stackings and RNN way of converting POMDPs into MDPs?
Yes. So yes, frame stacking is one way to convert POMDP to MDP. Okay, but it's not a perfect conversion. It's just an approximation. Like, but it is a good enough practical approximation for a lot of tasks.
So when you do the frame stacking or RNNs, the observations get stacked over time and they give a complete picture over the history.
Yes.
So we can assume that we get full information about the states.
Okay, that is what I was trying to differentiate. With frame stacking, like maybe let's say imagine like as a hypothetical example, let's say we stack all the frames we have seen so far. Okay, but that's very inefficient. But let's just say that we can do that, okay, in an efficient way. Now let's say you're in 10th time step, you're stacking all the frames from the first to 10th time step. Okay, now that doesn't mean you have access to the state representation. Okay, because maybe in these 10 steps you have not covered the entire state representation.
So we are stacking the observations and it might be similar to this.
Yeah. So for example, let's take like a four room kind of setting. Okay. Now let us say that there is actually an opponent here, and there's a door here, and you are here. Okay. And you have a limited view. You can only see like few steps ahead of you. Okay. You might take 10 steps and reach here. Even if you integrate all these state representations, you still don't know that there is an opponent waiting for you on the next side of the door, right? Like so you have partial observability still. So it is stacking or like using RNNs is not completely solving the partial observability problem. Like, so in fact, it's much more harder in these settings, like, because now the agent has to anticipate. Like, so the agent has to start like making decisions. So decision making under uncertainty. Okay, which is not the case with MDPs. Like, so especially if you have access to everything, right? Like, so now with partial observability, like, you don't know like things in the future, so you have to be very cautious about your planning. Like, so you cannot, like, for example, like if you're walking very fast or you're running, when you cross this door, like, you probably should not run or walk very fast. Like, maybe because there's an opponent waiting for you, like, you just need to peek and see if there's an opponent, and then maybe go back to a different room and so on, right? Like, so you need to be very cautious. Like, so the definition of optimal planning, like, or optimal policy, is going to be different. So like, it's also very difficult to find that optimal policy in this.
And when you have a replay buffer in these settings, there also we are kind of storing previous transactions.
Yes, usually using a replay buffer with this kind of like RNN setting is very difficult, like, because now you have to not just store the current transition, like which is state action reward next state. You have to store the entire history of like states observed so far. Like, so, but it's more of an engineering problem. Like, so you can do that efficiently, like, so by having a very complex replay buffer structure. Any other questions about partial observability? Okay, so in the next problem, that also something that we have already covered, is about state and action abstractions. Okay, now typically when we talk about like policies, like, so we talk about policies per time step. So this includes, given the next state and action, like given the current state, what is the next action? Like, which in the case of a robot might be just moving 1 degree. Okay, if you're going very low level, like to move 20 degrees, like you might require like more actions. Like, so to move from here to the door, probably you require 1,000 actions. Okay, now that is not a way to scale these algorithms, because you're unnecessarily making the problem harder. Like, sometimes thinking at low level is hard. Okay, so when we plan, like, we plan at much higher level abstraction. Like, so when you plan for the week, like, you don't plan what will I be doing on a Monday morning 9:45 p.m., 9:47 p.m. and so on, right? So Monday morning 9:45 a.m. or 9:47 a.m., right? Like, so like you will have a very rough higher level plan. You will say, okay, by Wednesday I'm going to finish my RL assignment, and for the remaining 2 days, like, I'll probably work on this other course assignment. Okay, then you start fine graining your plan. Like, so like, let's say you have 3 days for the RL assignment. Like, so you would consider, okay, so maybe today I should just code so that I can run experiments tomorrow and then write the report next day, right? And finally, when you go to the report writing stage, then you will plan, okay, so I should write this question answer first, like, so, and then this one and so on, right? Like, so we have higher level plans, and we always like try to like come up with fine-grained plans as we move on. Okay, but there are also a lot of things which we don't plan, and like they are just happening automatically. When it's automatically, like without your consciousness, right? Like, so for example, let's say you want to make coffee. Now, you know that you have to go and grab a cup, right? So you don't plan to grab the cup. Like, so you know that you have to turn on your like stove, right? Like, so there are a lot of actions that are very organic, and like, so that just happens naturally. It's simply as if it is hardwired in you, right? Like, so obviously we are not born with hardwired ability to make coffee, right? Like it actually requires, if you think about making coffee like one step at a time, it is actually a very complex process which requires thousands of steps. Okay, but we don't think it that way. Like we do higher level plans, right? Like so now, how can we design agents that can do higher level plans? Like so, I think that's probably one of the most hardest open problems in reinforcement learning. Okay, so there is a lot of work in the last 10 years. Like I would say we haven't made even like there is like, for example, there is no like one representative algorithm that I can teach in the class. So so we have a long way to go in solving temporal abstraction. Okay, so so this is, I think we covered this under hierarchical reinforcement learning. We talked about options and we talked about max Q, I guess, did we? And probably one more, I don't remember. So like basically we talked about like some simple ideas to have this temporally extended actions, but how to do that in a much more efficient way is an open problem, and there is a lot of work in the literature. I recommend you to go and read. Okay. Any question about temporal abstraction? Okay, so I think this pretty much covers the issues that we have already addressed in the course. Okay, so like, I think the first issue was something that we did not address previously, but now we are going to talk about some of the other issues like which we have not addressed so far. Okay, now one of the big topic for discussion is generalization. No. Okay. Now, in the case of supervised learning, it is actually very easy to define generalization. Okay, so so what do I mean by generalization in supervised learning? Like, so I give you a bunch of examples. You learn a model, like you learn a function f, which makes some which maps x to y. Okay, using some data set, training data set. Now, the question of generalization in supervised learning is, given a completely unseen x, how good is my model in making prediction y? Okay, now that is for supervised learning. Now, what do I mean by generalization in reinforcement learning? So maybe I'll get some opinions first. Like, so, like, what do you think is generalization in reinforcement learning? Generalizing from what to what?
How the agent will perform in a similar but different. The task is similar, but the
okay, so how would the agent perform in a task which is kind of similar but different from the current task? Okay, any definition for generalization?
This is on a higher level, like in terms of function approximators.
It could be anything.
In function approximators, given a new state, you'd like to know how well it.
Yeah, I think we have the same answer in the chat as well. So like probably a very low level generalization goal is, given a new state, like how do I generalize? Like this is within the same task, right? So any other definition? Yeah.
What if we change the goal state within the same grid? Let's take a 4x4 and then like change the terminal state.
Okay. I think that is kind of similar to the first suggestion. Like, so like you, like so far, like I think we discussed whenever we looked at grid words, like, so we always, even in your assignments, right? Like, I guess, like we always said, okay, so this is my start, this is my goal, let's say, and we are learning a policy, right? Now, what if my goal changes every time? Like, so how do I learn a policy? Okay, so which is similar. I'll try to categorize things like I think the first categorization is like the simple. Let's start with simpler one, like which is like generalization to new states. Okay, and the second one is generalization to new tasks. Okay, yeah, you had something. Okay. Any other generalization that you can think of?
You can also think about a policy. You can just reuse the policy.
Okay, well, I think that comes under generalization to new tasks. Okay, I think these are probably like two broad categorizations. Okay, so we already talked about generalization to new states, like when we were talking about functional approximation. So let us just talk about generalization to new tasks. Okay, now what do I mean by generalization to new tasks? Now, okay, so there's also another categorization, which is just the idea of like non-stationary environments. Okay, so when I have a non-stationary environment, it is also like generalization to new task, but the thing is like you have one task, but the task changes like very subtly, like so, or sometimes abruptly, like so it could be the transition dynamic which is changing, or it could be the reward function which is changing, but there is some change that is happening all the time. It just means that you can never converge, like so you should be constantly learning. Okay, now first let's talk about generalization to new tasks. Now, one of the limitations of like, well, first of all, like it is very, very difficult to do any generalization with tabular methods. Okay, so probably you can handle non-stationary environments with tabular methods, like say if you have a constant learning, but you cannot do generalization to new states or generalization to new tasks with tabular methods. So you have to resort to function approximation to do either of these generalizations. Okay, now if you talk about generalization to new tasks, okay, so how do we define a task? So in reinforcement learning, we would often define a task as just an MDP. Okay, now when I say I want an agent that can generalize to a new task, the goal is like a bit more ambitious because you cannot generalize to any task. Okay, so often when people talk about like generalizing to new tasks, like we will make an assumption that this MDP actually comes from a distribution of MDPs. Okay, like a family of MDPs, and like can we come up with a good like agent like which would solve any of these MDPs like in this task in this particular distribution, right? Like so now there are many ways to achieve it, like so, but maybe before that I'll take the question. So
Oh yeah, I just want to ask that things like sim to real, or like there are like some generalization tasks where you like change the background of is this can be categorized into like generalization to use tasks?
Yes, you can put that under generalization to new task. And in that case, I think there's some relationship between the simulated MDP and real world MDP, yes, right? Like, so they're kind of related, but with some differences. Yeah, that's a good example. Okay, so now how do I generalize across like a distribution of MDPs, right? Now, any ideas? Like, so how can we extend the current algorithms to do this generalization to many MDPs?
You can sample from
like for example, okay, so maybe I'll give you a little bit more like hint. So let's take Q world. Okay, so let's just take the grid world example. Okay, now we are going to use, let's say, Q learning. Okay, so which means we are estimating the values of the state. Okay. This is one MDP where the start is in the bottom left and goal is in the top right. And here is another MDP where let's just say start is here, goal is here. Okay, I could have another MDP where start is here, goal is here. Okay, so now I have a distribution of MDPs, like so each having different start and goal. Okay, now what does it mean to say this is the value of this state? Okay, because the value of this state is going to be different in each of these MDPs, right? Like so, like the value of this state in this MDP is going to be very high because it's very close to the goal when compared to the other two grid worlds. Yeah.
So you can try to learn the distribution of those MDPs, and like the overall value of that particular state would be, let's say, weighted by the probabilities of those MDPs.
Okay, but is that a good idea? So okay, so you're saying, okay, so I think if I understand correctly, the suggestion is like you just learn the value of the state irrespective of which MDP it comes from. So you're going to have some average value.
So I will like the starting point.
We need to have the values with respect to the start state. Somehow should encode that into the.
Yeah. So okay. So there are two solutions here. Okay. So but first let's talk about the average solution. So average solution is not optimal, like because we don't care about like the average value, right? Like so we actually care about. So the thing is like average solution could hurt the overall performance. Like when you act, you have to act purely based on the given MDP. Like so, like otherwise, like you're going to have suboptimal reward in what that MDP, and you're going to have suboptimal reward in all the MDPs. So on an average, you're going to get really bad performance. Okay. So which means that like we should go for a solution like what he suggested, like which is the idea of somehow conditioning your values also on state and action. Sorry, the start state and goal state, right? So now how do I do that? I think so given that I'm converting the project to a 4th assignment next year, so we should definitely have one assignment like where people think about more than one like MDP. Like so I think for the entirety of the course, we did not care about this problem, but this is a very relevant problem. Like so like you're like a lot of applications, like you're like you will be coming up with agents which are going to handle a distribution of tasks, not just one task. Yeah, you had something.
Yeah. So the question is that how can we condition the value on the start state and goal, or is the question of like how can we learn such conditioning?
Both.
Oh, I have like an idea for like how to learn such.
Yeah.
You can do like data augmentation things, like you can like randomly sample from that distribution of MDPs you care about and let the model to learn.
Oh yeah. So okay, that like if you want to learn, like yeah, you can sample from these MDPs. Like we're assuming that like let's assume that you don't have control over like the sampling process. In every episode, nature gives you a grid word. Okay, so like you have to learn to solve any grid word from this distribution of grid words. So okay, so here's the thing, like so as long as you have the right representation, these kind of things are possible to be handled. Okay, now this is why I said tabular methods are going to be useless here. Like so, because the problem with tabular methods is okay. Let me see if I can charge quickly for a minute. I did not expect it to go. Okay, I don't know if it is charging, but it's worth trying. Okay, so the problem with tabular approaches is like you are, okay, I think I'll charge in the break. Okay, so the problem with tabular approaches is like you're learning a value function for this particular state, right? Like so your state here is not good enough to handle the distribution of states, okay? On the other hand, let's say you are using a DeepQ network, which takes this complete grid world as image or in some representation. Like so, for example, they say the states is complete grid world as a 4x4x3 matrix. Okay, so where there are 3 channels in this 4x4 image. The first channel is pointing where the source is. The second channel is pointing where the goal is, and the third channel is pointing where the agent is. Okay, so let us say you are here. Okay, so the first channel would have a 1 here, and the rest is all 0. And the second channel will have a 1 here, and the rest is all 0, and so on. Okay, now I can pass this to a convolutional neural network and learn a representation, and then learn a value function. Okay, so now this value function is kind of conditioned on like where is the start, where is the goal, where is the agent. Okay, which means you are estimating a value for this whole situation in the grid world, not for that particular grid position. Okay, so now I can learn value function which says, oh, if I'm here and the goal is here, like probably it's a good state. Okay, however, you give me the same grid. Okay, let's take something like this. Okay, so let's take the second example. Now, if you're very close to the goal, so this is a good value, right? Like so. Now, if I just switch things and I'm still here, this network can generalize and say, oh, this doesn't have that high value because you are still close to the state, close to the start state. Okay, now you can handle this kind of distribution of MDPs like by just having right representation. So the first solution is like by just using right representation. Okay, now what are the other ways in which we could solve many MDPs together? So I think one of the problems with this approach is this might work for simple cases, like as the problem gets more and more complex, like so learning one policy for entire like distribution of MDPs, like so this is definitely a much more harder problem than like just learning one policy for one MDP, right? So but this is not the only way to handle distribution of MDPs. Like so, any other suggestions? Okay, there's a question in the chat. Okay, there are a lot of questions in the chat. Would it be possible to analyze the task first and find a way to represent? Okay, task 1 and task 2. Okay, so we are going to talk about this question, I mean, like after the break. I'll probably take the second question. Is it possible to, like, okay, there are a lot of questions coming up. Is it possible to apply this strategy in tabular methods? No, right? Like it's very difficult to do this with tabular methods. Like so, that's why functional approximation is more useful. There's another question. If we have partial observability, it somewhat forces the agent to generalize. Yes, generalization is even more crucial in partial observable situations. Okay, so we will take a short break and then discuss about a couple of other ways in which you could generalize to more distributions, more MDPs. Okay, but I want you to think about it and come up with some suggestions by 11:30. So